Hello and welcome back to Calculus 2. We are starting the chapter on power series. I mean power series, because this stuff is extremely powerful. It's used a lot in mathematics. There are courses that are based only on this stuff in the future. For those of you who are math inclined and want to do more, whole bunch of engineering depends on this, like electrical engineering. If you wish to do anything with electrical engineering, it will be impossible to do it without this stuff. It's the core of much of what's happening later. So if we are going to take analogy between what you learned so far in mathematics and these chapters 8 and 9, we would take a look at the sequence AN as being something that is equivalent to numbers. So you have a list of numbers, right? So that will be something that it's equivalent to numbers. And then you take the summation of AN. This would be something equivalent with addition of numbers. And if you are to take a look at the power series, that would be something as the functions. So we upgraded from sequences to series to now power series. So power series are still going to have your good old sequence AN, now called CN for coefficients. And you are still going to have summation, right, because it's a series. And as a new feature, there we go, you are going to have the x, which is the variable, right? So these things will have domains and intervals of convergence and all other cool things that the series on its own did not have. So it's a progression, right? It's the next animal. So what is power series? Power series is going to be denoted as I said, c to the n, x to the n. It can start at 0 and go to infinity, or at 1 or 7, whatever. So it's going to start somewhere, and it's going to push through infinity. So the first term for the power series is c0, right? X to the 0 is 1. Then plus c1x plus c2x squared plus c3x cubed plus, and it's going to go like this forever, because there is infinity. Now, I hope that you see family of polynomials here. This is a constant, right? The first term, it's a constant. And then if you take a look at the first two terms, you technically have mx plus b, right? If you take a look at the first two terms. They're just using different letters, but it's still mx plus b. So that's linear. And then you have quadratic, and the cubic, and the fourth polynomial, right? So there are polynomials, and all of them are there. And in a more general case, we can shift this left or right by simply adding or subtracting number directly to x. You know that from pre-calculus that you shift functions left and right if you add or subtract number directly on x. So in general, you can write summation cn x minus a to the n from 0 to infinity, which will give us c0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed plus ... forever. Now we will say that this power series here is centered at x equals a. It's centered at a. And we will see why we must have that. So now we are going to turn our focus to approximating functions. when I learned this, I was just blown away. I said, why did I actually learn anything else? If this exists and it's so cool. The idea is to take any function, we're talking exponential, trigonometric, right? And write it as this. What you're doing here is technically converting transcendental functions into polynomials. And polynomials are easy to differentiate, easy to integrate. They're a little bit tough for finding roots, right? Because we can find roots easily up to fourth order, and then after that it's a living nightmare. But calculus-wise, polynomials are the best creatures in the galaxy. I mean, yeah, e to the x, but polynomials. And then polynomials are also insanely easy to compute. You would rather compute 3 in a polynomial than e cubed, or at any point. So if I am able to take any transcendental function and change it into a polynomial, I am set for computation, integration, derivatives, everything becomes easy. The trade-off. The function is going to be equal to the power series only if you use all infinity of terms. Then they're equal. If you start chopping off things, you chop off after, let's say, fourth term, the equality between the two is lost. But you will see how quickly we get extreme precision. Some of you who took physics and you did the simple harmonic motion, you've seen the equation for simple harmonic motion, and that equation had sign in it, which means it's a nonlinear equation. And you heard your professor say, but for small angles we replace sine x with x, and then we just compute easily. That's the one-term approximation, which is what we are learning today. So you take sine x and you replace it with x, but you say for small angles. And why we can do that? Well, if you think about sine x, which looks like this, right, going forever, and you think about y equals x, don't you agree that in this region here, the y value for the line and y value for the sine have nearly same answers, right? So for about, I don't know, pi over 6, like 30 degrees left and right of origin, it's a pretty good approximation. And it's terrible over here, right? Because this is the actual value, which is -1. And if you look at this one, it's all the way up there somewhere, right? So that's where this shifting plays the role. I can find approximation, right, in that region there, and then, but we'll see how that works. So we can say sine x is approximately same as x for small x, and we'll see how we can figure out what that stuff is. So where do we begin? Well, you see that I took the function sine x and I replaced it with y equals x, and y equals x is a linear line. You know this from Calc 1. You better know this from Calc 1. It's called linearization, tangent line. So if I write the linearization from Calc 1, Lx equals to f of a plus f prime at a, x minus a, you better recognize your tangent line there. But what else do we recognize from tonight? We recognize C0 plus C1 x minus a. That's the first two terms of the power series. Power series will allow you to approximate functions now, not just with tangent line. They will allow you to approximate with quadratic and the cubic and the fourth degree and the fifth degree, as many as you need to reach the precision that you need. But you will see how fast this precision actually kicks in. So you will not have to use, 10, 15 terms. Usually 3 or 4 terms are enough to get good approximations for numbers you need. And you will have to play with the value a to line stuff up. So, where we go from here? Example. We're going to do Calculus 1 example where I'm going to approximate a function using linearization to compute a value. Which value do we want to compute? ln of something, square root or cube root of something, what do trig function of something, what do you want to compute? Pick something quickly. Trig? Okay, so secant of what? So we're gonna land at something. So okay, so give me secant of what? That's an exact value. I'm sorry? 0.2. Okay. Secant of 0.2. Great. So what is the close value that we can compute? A is going to be equal to 0 because secant of 0 is 1 over cosine of 0, which is 1 divided by 1 equals to 1. So I am picking A equal to 0 because that is the closest point that I can compute secant at without the calculator, and secant has a value there, right? So now all we need to do is to crank linearization. L of x is function computed at A. Actually, let me just spell out that f of x is secant x and f prime of x is secant x tangent x because we can. So now, what should I do? I write that the linearization computed at x is going to be secant computed at 0 plus the derivative computed at 0, which is secant of 0 times tangent of 0 times x minus a, which is x minus 0. Since tangent of 0 is equal to 0, we get that approximation is 0. Now, how much, if you use the calculator, I'm sorry. Oh, secant of, oh, sorry, secant of 0 is 1. Yes, yes, yes. I meant to say, yeah. We have it here, all the way on the top, that secant of 0 is 1. So use the calculator. Secant 0.2 should be computed as 1 over cosine 0.2 and use radians. And you will see that you will get a value that is, so 1 divided by, and then cosine 0.2. Make sure your mode is radians. How much? 1.02. So our approximation is 2 cents away. We used only one term in this case because the second term died due to tangent of 0. Why does this stuff work? Let's take a look at example that contains square roots. Easy to draw. So if I draw a square root function and I want to compute a value somewhere, I find a closed tangent line at the value I can compute. So value I can compute without a calculator, but I'm interested in this value x. It is what I need to compute. If you zoom in right? So this is your A, and this is your X. You see that linearization computed at X is very close to the function computed at X. They're not the same value, but they are very, very close. So that's why it's important to do linearization next to the point of interest. Hence A. If you are supposed to figure out how much is the square root of 15, what's the closest value that you can compute? 16. So you are going to use A equals 16 in that case. You are centering your linearization at 16, A equals 16, because that's the closest value you can compute without a calculator. How about ln 3? E. Very good. E. Because ln 3, E is 2.7, right? About. So that's the closest value. For ln 3, you use E. Now, figure out what E squared is. Like E squared, that's around 10. So ln 10, you will be computing with E squared. And E squared is easy to compute as well. Because ln of E squared is 2. Right? Because the power drops in front of ln, and you have ln E. Ln E is 1. 2 times 1 is 2. So your job is to figure out what is that one point which makes your approximation close to what you have to compute. And I would say in most cases that's obvious. Maybe ln3 was not obvious for some of you, but now it becomes obvious as soon as you hear it for the first time. So you have square roots, you have trig, you have all of these things. Imagine turning each one of them into a polynomial and then integrating and differentiating and doing all of these things easily. Now, what is this linearization, i.e. tangent line, from Calc 1? Well, it's just the first two terms from your power series. You can include the next term and the next term and the next term until you figure out many terms and come up with better and better approximation. The only way to come up with the exact number is to use all infinity of terms, but since we're not elves, we don't get to sit there and, right, with Legolas, calculate this forever. So I already said that this Lx, which is the f of a plus f prime of a times x minus a, is the tangent line. We can do better if we say c0 plus c1 x minus a. Better than that would be c0 plus c1 x minus a plus c2 x minus a squared, and then add one more term, and add one more term, and add one more term, going on. The question is, how do we compute these terms? And you guys can look at the proof in the textbook. It's not too complicated. But there is a formula which generates C0, C1, C2, and so on. And as you can see on the first line, it clearly involves derivatives. So the formula for C is going to be the derivative computed at A divided by the n factorial. So this is going to generate all of the C's that you might want. And you can see, it's 6 lines in the textbook, how to come up with that formula. So now I know that if I'm looking for the fifth C5 term is going to be the fifth derivative computed at A divided by 120. Now, you are taking a number and dividing it by 120. How tiny that thing is going to be, right? Very tiny, right? Which means that the fifth term doesn't contribute too much to the overall value, because you divide it by 120, and then whatever you got there, you add to everything else. So it doesn't contribute too much. So you already see that because of this factorial, it grows insanely quickly. You have 120, and then you have, after that, 720, right? Because 6 factorial is 720. Imagine dividing something by 720. That is also a tiny value. So it should be clear that these things pick up values quickly. So now we get to the, I mean, this is where the book really makes no sense in the way they did the sections. We get to talk about Taylor polynomial, and then we have 9.3 Taylor series. Same thing. So technically we're taking care of the both situations now. And this is technically 9.3 stuff. So what is happening here? There is the definition which says that function f of x is equal to the series of fn computed at a divided by n factorial times x minus a to the n goes from 0 to infinity. This is one of the most powerful things that you are going to learn in undergraduate mathematics. It is conversion between any function to a polynomial. Obviously, the derivative is the nth order derivative, meaning the 0th derivative, which is the original function, and then the first derivative, second derivative, third derivative, fourth derivative, and so on. By the way, for those of you who want to break your heads a little bit, go online and look up at the half derivative and 3 half derivatives and 5/4 derivatives and all that kind of stuff. Because over here we only deal with whole number. So we can use this to generate derivatives for the function and then generate coefficients, and that immediately creates, you have x minus a, that creates a polynomial. So we can apply this to any function. So naturally, we're going to start with e to the x, and then follow by sine x to see how these things are done. Maybe we should do sine x first, because e to the x has a boring derivative that repeats over and, let's do e to the x, go ahead, whatever. F of x is e to the x. I'm going to center this at 0, and expand using Taylor series. Awesome. I need a whole bunch of derivatives, and all of them are e to the x, right? Now I need to compute all of those derivatives at a. So first derivative computed at 0 is 1, and the second derivative computed at 0 is 1, and the third derivative computed at 0 is 1, and the fourth derivative computed at 0 is 1. So they're all 1. Now I need to plug, oh yes? That's a Maclaurin series, yes. When it's centered at 0. So Taylor is the overall general case, and Maclaurin series is the specific one which is centered at 0. So this is Maclaurin series now that we're doing, which is the, like the square is the special rectangle, right? Rectangle has all these different lengths, and square is the only one that has all sides the same. Circle and ellipse, right? So this is that thing, Maclaurin and Taylor. So Taylor is the overall, and then if you say a equals to 0, it's Maclaurin. Okay, so now let's write this thing up. So e to the x will be approximated by function computed at 0 plus the first derivative computed at 0 divided by 1 times x minus 0 plus the second derivative computed at 0 divided by 2 x minus 0 squared plus third derivative computed at 0 divided by 3 factorial is 6. You know what? Let me put these factorials in since I'm not computing yet. 3 factorial x minus 0 cubed plus the fourth derivative computed at 0, 4 factorial x minus 0 to the fourth. And this is going to go on forever. So you technically quit writing when you become bored. You can put as many terms as you want. So now that is equal to e to the 0 is 1, plus we already figured out that the coefficient is 1, so you have 1 divided by 1 times x, plus 1 divided by 2x squared, plus 1 divided by 6x cubed, plus 1 divided by 24x to the fourth, and that's going to go forever. And now I can write, finally, that e to the x is approximated by 1 plus 1 over x, plus x over 1, so it's just x, plus x squared over 2, plus x cubed over 6, plus x to the fourth over 24, plus, and it's going to go on forever. So here is your Taylor expansion for e to the x. Of course, you have a calculator to compute stuff, but go back 100 years. This was it. This is how you compute e to the, let's say, 0.3. To compute e to the 0.3, you don't take the calculator out. You say, okay, that's 1 plus 0.3 plus 0.3 squared over 2 plus 0.3 cubed over 6 plus 0.3 fourth over 24, and these values you can compute by hand. What was there for engineers before calculators? What was used to create the calculator? There was a book. There was a book called log tables. And that you carry that book, and that book has tables of numbers. ln of 0.1, ln of 0.2, ln of 0.3, and you actually scroll through the book and you find what ln of 7.8 is, because it has there, 6, 7 decimals given. Now, how did they compute that? That's pre-calculator era, pre-computer era. This is how they do it, right? Now, who did that? Who had all the time in the world that was bored out of their mind to sit there, compute ln 5.6 to 6 decimal precision, and then go and say, okay, now I compute ln of 5.7 using this, and then 0.8, and then 0.9, and then maybe even in between. I don't know how many. What do you think? Who? No. Nope, none of them had time for that stuff.
Will it just be the same difference for everyone?
Nah, it's not a linear function. Really? Did you just say Jesus? Captains of ships. Yeah. So, what are you gonna do? You're on a boat for 3 months. You know how to do this stuff, but then you're bored. Like there's just so many executions you can have in a day. So you sit and you're not the one who's washing the deck and tightening the ropes. So you sit, you eat your fruit all day, stay hungry. I mean, stay healthy. That's what I want to say. And compute this by hand. We can honor those times right now because this is 1 plus 0.3 plus 0.09 divided by 2 plus 0.0027, sorry, one extra 0, 27 over 6 plus 0.0081 over 24 plus, it can be done by hand, it's not a problem. That's 1.3 plus 0.045 plus cancel by 3, 0.0045, right? Plus, and we are up to the point that no one cares actually. Now we use the calculator. Both of these are divisible by 3 at least. Are they divisible by 9? No. So that would be 27 over 8. 27 over 8. Yeah, 3 something. So it would be 0.0003. 7, that's 2, that's 5, 8, and 5 goes 4, 5, 6 times. So 6 something, whatever. So there you go. Now you add these numbers, and you get 1.349, I think, 6, whatever. Now go and put e to the 0.3. It should be close to this number, unless we broke mathematics or something. I hope. So my calculator here, Android calculator, gives 1.3498588.076. This is what the calculator gives me, and this is what we computed by hand without doing any stuff. So I understand that today this method of calculation is something that we would not do because we have access to calculators on our cell phones and smart watches, and technically anywhere you look, you have access to a calculator. But at least it's cool when someone says, what do you know? Oh, I can compute e to the 0.7 by hand. Right? What do you know? I know how to use calculator. And what do you do when your battery runs out? And you're stuck on a desert island? And you need to compute the value? Yes? When did Taylor Swift come out? Hence the name, and then we have the and we have 1800s. So yeah, you're technically 200 years behind still. I know. Such is life. You're catching up quickly. So I mean, you were about 400 years behind when you did Calc 1. Now you're about 200 years behind in the Calc 2. Calc 3 is the same. Differential equation is pretty much the same. Linear algebra pushes you into about 120 years behind current mathematics. It's awesome. It's the one that is happening now with hyperdimensional numbers and things. Topology and yeah. Lots of fun to be had. All right, so we got the e to the x. Now, you know what I want to do? I want to graph these two things in Mathematica to see how well their graphs agree. Because I can. And the way I'm going to graph it is I'm going to graph every single one of these separately. All right? So this one, this one, this one. Each time when I graph a function, I'm going to add another one. So let's see how that works over here. I turned off syncing with the cloud, and it's not crashing anymore. So I'm happy in that department. All right, this is Mathematica. Hopefully you all have this installed and running on your machines. You hit on the plus. You can use Wolfram Alpha Query, it's fine. And just talk to it. Graph e to the x and 1 plus x and 1 plus x squared divided by 2 and just keep adding the next term. So I want to copy this. Plus x cubed divided by 6 and no. And x to the plus x to the fourth divided by 24. Now you can go many. So we're going to get all of these different graphs on the same viewing window. You see the progression. Each one I add more and more. And here's the plot. So is it possible to make this? Yes. All right, so I believe that e to the x is the blue one. So you have clearly the orange one is 1 plus x, right? Because it goes to 1 and it's linear straight line. So that's 1 plus x. And then you see the green one, which would be the next one, is better. And then this one is better and this one is better. So definitely e to the x is the blue one because you see how that one goes on the axis over here. We can't even see the purple one because probably it lines up with the blue one very well on this interval 0 to 1.5. They do fan eventually. The more terms you keep, the approximation sticks longer around the function that you are approximating. So you see how the first approximation, so you are trying to look at the blue line and the orange line. You see that, you know, for let's say up to 0.3, they're pretty good match. But then they start diverging one from another, and you see over here that they are already really far away. But that was just the first approximation, right? And you see how much more improvement you get as soon as you include another term. So this one is just 1 plus x, and this one is 1 plus x squared over 2. And look how closer it went to the blue line. And this is the one that has a cubic, that one. And the purple one you can't even see because it's writing the original function. However, if we sufficiently extend this, it should show.
that bottom graph as well?
Oh yeah, the bottom graph. Thank you. I didn't look at the bottom graph. So you can see how bad at 10, how bad linear graph is. And then here is the next one, next one, next one. You see that these guys are still far apart. So that's why you can't approximate e to the x, right, around 0 and do calculations for 5 and 10 and so on. Doesn't work. This is where you did approximation. A equals 0. If A equals 0, that means in that neighborhood, these guys are going to be close, and everywhere else, they're going to go crazy. Now, can I use the same functions and only 3 terms if I want to compute at 5? Sure, but you have to drag x minus 5 in each one of your calculations, because that shifts. And then everything will be nicely lined up here, but they will be diverging around 0 and diverging on the other spots. That's what that A is, to shift the good values, good match, to shift the good match where you need it. All right? So let's take a look at sine, and technically that's it. We'll have one more class next time for chapter 9, and chapter 9 is done. I hope you're not disappointed, but that's what it is. If anyone wants to follow me to the event, you're more than welcome to learn about the amazingness of the world.
If anyone wants to vote for me for vice president of Phi Beta Kappa, follow me.
Well, only members can vote, right?
Yeah,
Yeah.
members.
All right, so f of x is now sine x. The first derivative is cosine x. The second derivative is negative sine x. The next derivative, third derivative, is negative cosine x. The fourth derivative, which is where I stop, is sine x. And now you see it's a loop. If I'm computing this again at 0, then function of 0 is 0. Function in the derivative computed at 0 is 1. The second derivative is again 0. Third derivative is negative 1. Fourth derivative is 0, and so on. So sine x is approximated by f computed at 0 plus f prime at 0 times x minus 0 plus f double prime at 0 divided by 2 x minus 0 squared plus the third derivative computed at 0 divided by 6, which is 3 factorial, x minus 0 cubed, and we put the fourth one, which is the fourth derivative computed at 0 divided by 24, x minus 0 to the fourth plus dot dot dot. Plug everything in. Sine x is approximated around 0. 0 plus 1 times x plus 0 times x squared minus 1 over 6 x cubed plus 0 times x to the 4 plus dot dot dot. So this is what we get. So sine x is approximated by x minus x cubed over 6. And then I'm going to give you other terms, even though they are not here because I know them. It's plus x to the 5 over 120 minus x to the 7 over whatever the hell 7 factorial is, plus x to the 9 over 9 factorial minus dot dot dot, and it's going to go like that forever. There's your expansion for sine. Do you see a cool feature here? Yes, all exponents are odd. Do you remember how you had to memorize in pre-calculus 2 that sine was an odd function? And when you asked why, we just say because it is. And if you get to calculus 2, you will eventually know. All exponents are odd. 1, 3, 5, 7, 9. Cosine will have all even ones. And why is the derivative of sine cosine? Because when you take derivative of each one of these, it's going to directly fall into the cosine series. And you'll see that. That's actually what we do in 9.4. Derivatives and integrals of these, which is you write the string, you take the derivative of polynomial. So if you are to integrate this, this goes into 1, this goes into x squared, x to the 4, x to the 6, and that's 2, 4, 6, cosine is even function. All of mathematics falls in as soon as you learn this. So we're going to have a lot of cool things to realize as we continue with this chapter. Your job for the next class is to expand as many functions as you can to get used to the process, because all of this stuff is now new. You have to memorize the formula, which says that the nth derivative divided by the n factorial times x minus a. You also have to figure out what are the cool values and proper values to pick to do these things. That's it for tonight. I'm going to just say goodbye to the stream.